everybody. Thank you very much for being here. This is a little story about a tiny country in sub-Saharan Africa that found a treasure. And it's a very practical example, and water-stable isotope methods have been one core pillar of these investigations, not the only one, but they have really helped for answering this really practical related question. So we are in Namibia, and this is about a deep-seated transboundary freshwater aquifer, and whether it is a fast remedy or a strategic reserve. This research has been done a couple of years ago together with the German Federal Institute for Geosciences and Natural Resources, and they have been working since many years with the government of Namibia to develop and research water resources in this really water-scarce country. All right. As motivation, this is still how water supply looks like in northern Namibia and in many other sub-Saharan areas. So on the left side, you see hand dug wells, which are pretty common. They are also used by both cattle and humans. So it's not always the cleanest water. On the right side, you see old riverbeds where the people dig down to they make like a funnel shape until they reach the old riverbeds that have sometimes some fresh water. Then there are sometimes surface water channels, such as here in Namibia, the Kunene or Shakati Canal. And often the distances are also really, really far from those well fields to home. And sometimes they have donkeys to transport it, sometimes they just carry it. This at least was the picture about 7 years ago. I don't think it has changed massively. But in 2011, the BGR made a huge discovery together with the government of Namibia. In Right region in northern central Namibia, there was a huge aquifer discovered. It was a coincidental finding at that time. And people estimated roughly for how long this water could supply Namibia, and they came to estimations of 400 years of water for water supply of the whole Namibian population. Now you have to know Namibia is not huge. It has 2.5 million people, and we're speaking of domestic water supply here. If we use it for irrigation and for developing irrigation schemes, we end up somewhere here, 15 years. Anyways, this is a huge water resource that was discovered. And you can see here the lower headline. This is all from real newspapers. Scientists urge sustainable development of Namibia's newly found aquifer. And at that point in time, the Namibian government made a very smart decision. They said, we will not open this aquifer for domestic or agricultural supply. We will first find out if this aquifer is recharged, and if yes, how it is recharged. So here on the left side, you see again the position. So this is a transboundary catchment here. The southern part is Namibia, the northern part is in Angola. And some of you might know the Etosha Pan. Some characteristics of these, or initial characteristics of this aquifer, were it was seated 250 to 350 meters deep, but it was sub-artesian, and that means the water is under pressure, and if you drill a borehole in, the water will go up in that borehole. And in that case, it was so much pressure that it went 20 meters below soil surface. This is a major advantage when you provide drinking water and when you have to pump water, because you don't have to pump it from 300 meters, you only need to pump it from 20, which saves a lot of energy. That water also had drinking water quality, and by 2012, the extent of this aquifer was unknown because that was the only deep core that they were drilling at that time. Now they extended this a bit. So the questions were, where does this water come from? And is this aquifer still connected to the hydrological cycle? And if it is connected to the current hydrological cycle, what proportion of this water that sits deep down there, ready for being used, is renewable? This was basically what we were doing in this project, and I had a little part in that. At first, we created a conceptual model. There was from the geologic core, there was a lot of geological information in the lithologs. So basically, the conceptual model you can see on the right side, we have a couple of aquitards in between, and we have different groundwater aquifers, so at different levels. The upper one is a salty aquifer that is not ideal for water supply. But here you can see this lower aquifer. And now the question is there any recharge or is there no recharge? If there's no recharge, it means it's a fossil aquifer. Is this aquifer recharged by direct infiltration of water, which would mean it comes from above and infiltrates very slowly, 300 meters? Or is there a recharge area that is far away from the actual position where this aquifer was discovered? And of course, it can also be a mix of all of these methods. So let me speak about first. Actually, this was my PhD topic. We were supposed to provide better estimates of the direct infiltration, which means the water that is coming from precipitation and infiltrates to the aquifers. And for this, I will not get too deep methodologically, but we used an incredibly easy method for that. We used stable isotopes, but we did a little trick. We enriched them and used them as an artificial tracer. So instead of a very small concentration of 0 point something, we applied a huge concentration of heavy water isotopes, which you can see here. And this was really done on very tiny plots. We added this water before the rainy season and then waited until the rainy season went over this study area and then tried to find our tracer back deep in the soil. Then we know how much it has traveled during that time, and that we can use to parameterize models and also to estimate recharge directly. So here you see an example on the right side. You see the deuterium scale, and it's a gigantic amount of deuterium or a gigantic concentration of deuterium we applied here at the soil surface. And we took another profile where you still see a very high concentration, and the lower blue is the position of the tracer peak after the rainy season at 5.6 meters, more or less. From this, we can directly estimate annual recharge, and this is what we did also. And we use this information for soil vegetation atmosphere transfer models. We parameterized them, and then we could come up with long-term recharge rates. This is an average of approximately 15 millimeters per year, which is quite substantial. But this is a sandy area where water infiltrates really fast, and it's a bit higher what we expected initially. So there is some direct recharge, but we could exclude it as important for the deep aquifer because of the geology. So there are a number of aquitards, and it's very, very unlikely that this water infiltrates 300 meters deep. And the second option is, does this deep water come from somewhere else? So could there be a recharge path from somewhere else? And here's where other isotope methods, not necessarily only stable isotopes, but also isotopes come into play. So we did age dating here of this newly found water, and we came up with 11 potential scenarios where the recharge could come from. And with both this information, we parameterized a hydrogeological model that can calculate flow paths and all of these things. And we calibrated it with the estimated groundwater ages. This worked pretty well. And from all of these scenarios, we came up that the most likely scenario is that water infiltrates at the foothills of the Angolan highlands, which is in the north. So it's not in Namibia, it's in another country, which creates another water management challenge. It infiltrates there where it rains a lot, and then slowly flows towards Namibia. The recharge amount of that is 1% of the annual rainfall, which means this deep aquifer has a current recharge path It's not a huge amount of water, but considering the size of this aquifer, it's still substantial. And right now in 2023, they opened up this water resource for the local population. And at the moment, 20,000 people in this northern area are supplied